There we go. Chapter 3 stuff. But we're not there yet. Chapter 3 stuff, but this is 151. We won't do that. We will do this. All right. Genesis. Somebody sent me, I've gotten a couple messages through Blackboard, and fortunately, when someone sends me a message through Blackboard, it shows up in my Outlook. What I found over the years is that if I've got one or two places to check, then I'm good about it. Once I get a third place where I need to check stuff, I shut down and only check one. So I do eventually see it, but I'm not necessarily, I don't know what the time lag is between you're putting a message in Blackboard and am I getting the message in Outlook. So it's something that's more critical, I recommend Outlook. However, I'm also not used to getting messages through Blackboard. So you sent me one earlier and I started to reply and then I thought, oh, why don't I just wait till class and if that works for you. Sorry, I'm not trying to put you on the spot. If we're talking about forces, which we are in chapter 2, if I have a 10 Newton force acting on a box, there's a net force on it. It's going to accelerate, as we will see in chapter 4. This is a 2 kilogram box. That the net force acting on it is equal to the mass of the object times the acceleration. This is the formula I think is in it. What I consider the most important formula in all of physics. So the math problem here would be 10 is equal to 2a. That's the math problem. How would you solve for a? So divide both sides by 2, and we get a is equal to 5, and this would be meters per second squared. Some of this we'll get in more detail in chapter 3. But this thing is going to accelerate. And accelerate means the velocity is going to change. In this particular case, it's going to speed up, assuming that it starts at rest. If I take that same box, and I have 10 newtons pushed that way on it and 10 newtons pushing that way on it, the total force is 0. Now some people look at that and say, put 20 newtons are pushing on it, but remember, we are adding vectors here. So in essence, I'm just going to make to the right a positive, because it's a one-dimensional problem. I can get away with just a positive or a negative to indicate direction. I don't have to use I hat or J hat. So the math here, my total force would be 10 newtons, positive if you wish, positive 10 newtons, plus negative 10 newtons, 0 newtons. So the total force is 0, acceleration is 0, velocity won't change. Which means if it starts at rest, it will stay at rest, or if it's already moving, it will continue at whatever velocity it was going. Dramatic pause for questions. All right. Let's add just a smidge of realism. Make it a 2 kilogram mass. I'm pushing on to the right with 10 newtons of force, pushing on the, we'll just keep it like that for now. This was just, I have a universe with a 10 kilogram mass on it and the force pushing on it. Now I'm going to put it on ground. Physical example, here we go. that got in the way. I have a couple of forces acting on this. I have this 10 Newton force pushing on it. So, and we will get into definitely more detail on what I'm now doing as a force diagram, but if I have 10 Newtons pushing this way, it has weight, which is going to be 19.6 Newtons acting down. Right now, just sort of believe it's going to be 19.6. We'll get into why later. But it's not falling, so something's holding it up. The ground's pushing up on it. So the ground's pushing up with 19.6 Newtons. So vertically, it's balanced out. Horizontally, it's not, so it's going to accelerate at 5 meters per second squared, just like this problem. Now I'm going to take that problem, sort of combine some problems there. So now, when I draw something like this, the ground like this, if it looks like I intended to draw it level, I did. We're not going to play the game of it's at a 1 degree angle and you missed it. I'm not doing that. If in doubt, just ask. But that's supposed to be level ground. I'm pushing on it with a 10 Newton force here. It's the 2 kilogram box. And another force is acting this way with 10 Newtons of force. If I did the force diagram, what are the forces acting on the box? I have its weight acting down, 19.6 Newtons. I have 10 Newtons pushing this way. I have 10 Newtons pushing this way. And then I'm going to have a force upwards from the ground, that's what's holding it up, of 19.6 Newtons. What is the total force acting on the box? I saw one hand gesture, that's correct. I've seen 2 hand gestures, that's correct. It's okay to say it out loud. There we go. You can say it with more confidence also. And in unison would have been incredible. Next time. So the acceleration is 0, which means the velocity won't change. Now, if I change it just slightly, so I now have a 2 kilogram force. All right, whoa. Strike that. That might be worth going in and editing that out of the video. I have a 2 kilogram mass. Kilogram is not a unit of force. I have 10 Newtons pushing to the right. And this other 10 Newtons is down at an angle. Is it in equilibrium? Is the total force 0? Gut feeling. All right, I got 2 people shaking their heads no. A lot of other blank stares. Or just, if I wait long enough, he'll just move on without calling on me. Who thinks that the total force is 0 now? I thought you said it wasn't.
Well,
who thinks the total force is still 0? Who thinks it's not 0? All right, got a little bit more, and then the others are just sort of waiting to see which way the wind blows. It's okay to make mistakes. It's okay. It does not make me think less of you as a person. Anyway, that came across worse than it intended. It was supposed to be a lighthearted comment, so I apologize for that. All right, it is not in equilibrium because this 10 Newtons that's here, that's pointing at an angle, not all of it is horizontal. Some of it is down, some of it is to the left. Now, in a 151 class or a 251 class, I would give you an angle and you would calculate it, but we're not going to calculate how much is to the left and how much is down. I'm just going to sort of give that to you. So I have the weight acting down, 19.6 Newtons. I have that 10 Newtons acting to the right. I have this one I'm going to break up and I'm going to say that's 6 Newtons acting this way and 8 Newtons acting down. And so now the floor has to exert more than 19.6 Newtons because I now have 27.6 Newtons acting down, so unless the floor is going to break, it's gonna be exerting that up, so this becomes 27.6 newtons, just the sum of those two. So I'm still in equilibrium vertically. This thing is not going to accelerate into the ground or come off the ground, but horizontally, it's now out of balance. It's going to be 10 newtons, ultimately 4 newtons acting to the right. Questions to hear about to connect it to the rope exercise we did? So in the rope exercise, when it was touching the ground, or at some point when, I forgot who was pushing down. So when Genesis was pushing down, at some point she sort of stopped. Let's just take a moment of when she stopped without touching the ground. If I look at that point and this, if I look at that, the scenario there, we had a person here, and then the rope was sagging, and then the person here, which I'll just represent as an arrow. If I'm looking at that point where Genesis was touching, I got 3 forces acting on it. I got tension pulling this way, tension pulling this way, and then this, what's called a normal force acting down. So I got this point on the rope, it's being pulled this way, it's being pulled this way, and it's being pulled down. Realize that some of this force is to the right, some of this force is up. If it is, the direction of that tension is right along the rope there. So if it's a really long rope, that's going to be a small angle, which means almost all of it is going to be to the right. The larger that angle is, the more of this force is going to be vertical. So this might be 2 newtons, this might be 20 newtons, and this might be 20 newtons. But it still might balance out if this angle is small enough. So I should have picked things that I could do in my head, but I can't, so I didn't. So I'm going to make some numbers up here. So this 20 Newton force, I'm going to break up into horizontal and vertical. Some of it is to the left, and let's say that's 19 newtons worth there. Some of it is up, and I'm going to change that to 19.5 newtons and 0.75 newtons up. And then the same over there. If Genesis was in the middle, it should be pretty close to the same. So 19.5 newtons. Oh, that should have been 1 newton there. I wanted to do math, make life easier. So 19.5 to the left, or right, as kids say today. To the right, another 1 newton up, and then I have 2 newtons down. So we had another equilibrium point. Most of the effort was spent fighting each other. Very little of it, because of the angle, was fighting Genesis. And so that's why she was overpowered, especially early on when they exerted nothing vertically. It was very easy to start moving it down. If they had been closer together, you know, I've been practicing drawing. You might have seen me the other day trying to draw a picture from a picture, and I still resort to stick figures. Tried to learn how to tie knots during the pandemic, and still resort to the square knot and the granny knot. Now, if they had been much closer together, so the rope was like this, then their force is now this way, much more of it is vertical, so they don't have to exert as much force to stop it. So the more vertical the force exerted, the more of it is, you know, you break it up. Some of it's up, some of it's to the right. Less of it is wasted fighting each other if they had been more vertical. So that's why I had a long rope, so that they would never get to that point, that they stayed with most of their force acting horizontally. Did that answer your question? That was not a convincing try. Are there questions? All right, I'm gonna let it sit there for now, and hopefully we can, well, we're dealing with forces in much more detail, so hopefully it'll clear up, or you can send another message to me, and we'll hopefully get it worked out.
When they're pulling opposite, do they cancel each other out as well?
If you have if they're opposite
And they're equal?
and equal in magnitude, yes, they will cancel each other out. They neutralize each other.
Usually.
So the net result is 0. And I'm probably going into more detail if just other students have had issues. It's not like those forces disappear, it's just like they don't, the net effect is 0. Just,
So because it was 0, is that why she was able to push it in the middle?
yeah, at the point, or close enough to 0, or she was, because almost all of their force was horizontal, very little of it was vertical, that's why she was able to touch it, is because, for the most part, they never quite got to equilibrium. They never could match the incredible brutal force of Genesis. All right, let's talk some specifics. I'm going to hit some of the words that I just used, and we are going to talk about forces and force diagrams. So, the forces that we will be dealing with in this course I have this little F down, I'll make references to that. This is just a checklist of the forces we'll deal with. F stands for friction. T stands for tension. O stands for other. I needed a vowel, and we do some simplifying in some cases. We'll get there. W stands for weight, or in general, gravitational force. And N stands for normal force. As those are nouns, normal is an adjective, normal force. The letters that I use when I represent them. For friction, I use what I refer to as the Baroque F. It's just a sort of a fancy F like that. It's a little extra scrolls. That's just the symbol that I'm using, just so that you can keep track of what I'm doing. For tension, I used to use a capital T for tension, but we will deal later near the end of the course where we need to deal with period and tension, and period, which is a time period. I use capital T for that, and so instead of using capital T now and then later going, it no longer stands for that, it stands for something different. For tension, I use F sub T, capital F sub T. Weight, I use a lowercase w, or the generalized gravitational force, which we'll get to in chapter 9 or 10, use F with a lowercase g subscript. And normal force, I use the letter Y. Now, it might seem bizarre about why I use the letter Y, but I do it for 2 reasons. 1, my high school physics textbook used the letter Y and it sort of stuck. And 2, we don't use capital Y for anything else. If you look at upper and lowercase our letters and Greek letters, we have 100 characters, and at some point you have to start repeating. So whenever I can use a letter that we don't use anywhere else, I'm taking advantage of it. Now, there are special rules of when these forces show up and when they don't. Weight, for example, Actually, let me do the general gravitational force. If I have two masses, there's a gravitational force. There's a gravitational force between any two masses. Between you and the person next to you, there's a gravitational force drawing you closer, but you're strong enough to fight it off. Because the gravitational force with masses our size is incredibly tiny. However, there are some gravitational forces that aren't tiny. Between me and the Earth, that is a large enough force to keep me down. So weight happens when there's two masses. I have one mass. Let's see if I can actually write in legible letters. One mass that is small and near a large mass. And when I mean by small and large here, large, I'm talking planets and moons. Small, elephant would be small on the scale. Blue whales, small, compared to the size of the Earth or the Moon. Tension, the requirement for tension, so these are requirements. For tension, I need a taut rope, chain, something that's pulling. For friction, I need two objects touching. We're not dealing with air resistance, and so objects do need to be touched. Even with air resistance, you have to be touching the air, but it does require contact. Two objects touching with desired relative motion. We will definitely get into more detail about what I mean by desired relative motion. The relative part is that relative to the object it's touching. It doesn't matter if